pragmatically, how do you measure the mass of an object? How can you tell if one object is more massive than the other, if you've got two objects to experiment with? Like if you just got two boxes and they're exactly the same size, how would you be able to tell which one is more massive or if they're the same mass?
One usually weighs more than the other.
Yeah, typically we would weigh it. The one that weighs more is more massive. But the problem is that relies on gravity. And mass is not just about gravity. The more massive objects will experience more force of gravity. So weighing it is a reliable way to compare the masses if you have gravity available. But let's say you don't have gravity. Let's say you're just out in deep space on a space station and you have two boxes and you want to figure out which one is more massive. Is there any way you could compare their masses without needing to refer to gravity? Like if you're just floating here in space and there's a box and there's another box, and from outside they look exactly the same, but let's say one of them is empty and the other one is full of water. Is there any way you can tell without opening the box which is which?
Could you possibly apply like a force to it and see which one moves the fastest or the furthest?
Yeah, if you apply a force, and I wouldn't necessarily say the furthest, because in the absence of any other forces, they're just going to keep drifting forever until they hit a wall or something. But let's try that approach of applying a force. Let's say you apply the same amount of force to both of them. You just punch this one and punch this one exactly the same. So you're applying the same force to both. What happens to an object when you apply a force to it?
It will move in the direction that the force was applied to.
It could start moving. Like if it's at rest and you apply a force, it's going to start moving. But force doesn't always cause motion exactly. Like let's say there's an object already in motion. If there's an object is already in motion and you apply a force to it, what does that do? You wouldn't want to say your force is causing it to move because it was already moving. But what does the force do to it? Yeah, it could speed it up. If you've got an object that's moving and you apply a force in the direction it's already moving, it's going to speed up. Or let's say you've got an object that's moving and you apply a force in the opposite direction. What's going to happen?
It's going to slow down.
Yeah, it's going to slow down. If you apply enough force or a force for a long enough time, it might even come to a stop. Or let's say you've got an object moving in one direction and you apply a force perpendicular to that. What would that do? Like if you've got an object moving to the north and you apply a force to the west, what would happen?
It'll move northwest.
Yeah, it's going to be moving to the northwest instead. You're changing the direction of motion. So this is really what a force does. A force can change the velocity of an object. A force changes the either how fast it's moving, makes it go faster or slower, or changes the direction it's moving. And since velocity counts as a vector, both of those, change in speed and change in direction of motion, both of those count as a change in velocity. So this is what a force does. Force causes change in velocity. And specifically causes a change in velocity as time passes. So we should really say force causes a rate of change in velocity, delta V over delta T. And what do we call that rate of change? What is the change in velocity over the change in time? Yeah, that is acceleration. And you can refer back to the chart of information on motion as well if you want to see that on math.ncheese.org. Force causes acceleration, which also counts as a vector quantity because acceleration has a direction. So this is really I think, the best way to think of force. Force doesn't cause motion. Force causes acceleration. Force causes a change to the motion of the object. If the object is not moving, then maybe a force causes it to start moving. If it's already moving, maybe the force causes it to change the way it's moving or causes it to stop moving. But a force causes a change in how fast it's moving and or the direction it's traveling. In other words, it changes the velocity. So let's say you apply a force to both of these mystery boxes. They're both going to accelerate. But are they going to, what would it tell you if they both accelerate the same rate? If you apply the same force to both of them and they both accelerate at the same rate?
They have the same mass.
Right. If they're both accelerating at the same rate because of the same force, then they both have the same mass. If they have different masses, how would you be able to tell?
Different acceleration.
Right. They'd have different accelerations. So let's say one of the boxes accelerates very quickly. You apply this steady force to it, and its velocity increases very quickly. And the other one, you apply the exact same force, but it accelerates more gradually, more slowly. That it is getting faster, but it's getting faster at a very gradual pace. What would that tell you about their masses?
The second one would be heavier.
Yeah, I wouldn't necessarily say heavier though. Yeah, because heavier usually refers to weight, gravity. But yeah, the second one is definitely more massive. The first one is less massive. So this is a small mass. And this is a larger mass. And I think this is probably the best way to think about mass when we're studying motion. Mass is all about how difficult it is to make it accelerate. A larger mass is going to get less acceleration for the same force. A smaller mass gets more acceleration for the same force. Or to put it another way, if you wanted them to both accelerate at the same rate, if you wanted these to both accelerate together, the one with more mass is going to require more force to make it do that. And what equation ties all these together? How are force, masses, and acceleration related? Yeah, force equals mass times acceleration. This is really the key here. Force equals mass times acceleration. And this is really just applying more detail to what we were already saying, that force causes acceleration. You apply a force, you get acceleration in the same direction. And the more force you apply, the more acceleration you get. In fact, as it turns out, force is proportional to acceleration. Apply 3 times as much force, the object accelerates at 3 times the rate. So that means force equals something times acceleration, and that constant of proportionality is just mass. So mathematically, this is what mass is. Mass is the constant of proportionality in the relationship between force and acceleration. The more massive an object is, the more force you need to make it accelerate at a certain rate. Or alternatively, the more massive it is, the less it accelerates per unit of force you apply. So I find it very useful to think of mass as being a difficulty level. More massive means more difficult to accelerate. And of course, any force on any amount of mass is going to cause acceleration. It's just that the more massive the object is, the slower the acceleration will be. And strictly speaking, this should be talking about net force. There may be several forces acting on an object. In fact, there usually are. But the important thing is not any one of those forces, but the net force, the total force. Sometimes also written as the sum of the forces. So the net force, or the sum of the forces acting on that object, not the forces from that object on other things, but the forces acting on that object, cause acceleration. And mass is the constant of proportionality there. Mass is how difficult it is to make it accelerate. So going forward, throughout the entire study of motion and beyond, anytime you hear the word mass, think of it as a difficulty level. More massive means more difficult to accelerate. And this also ties back into the idea of momentum. Because we're defining momentum in the first place as mass times velocity. Velocity is describing the motion of the object. Mass is describing how difficult it is to change that motion. So momentum is a combination of the motion of the object and how difficult it is to change that motion. And that's really all it is. It's just the motion of the object combined with how difficult it would be to change that motion. And another very useful way we can combine these equations, we usually write net force equals mass times acceleration. But what does acceleration actually mean?
Change in velocity over time.
Right. So if we make that substitution, so force, net force, total of all forces acting on the object equals mass times acceleration. We usually call this Newton's second law. Newton's first law is basically just what happens if there is no force. Newton's first law says if there's no force, then there's no acceleration. Honestly, I've never really been sure why that's listed separately. If you know Newton's second law, you can just plug in 0 for force and 0 for acceleration, and you immediately get Newton's first law. So I don't know for sure why Newton's first law is listed separately, but Newton's first law is just if there's no force, then there's no acceleration. And if there's no acceleration, then there's no force. Newton's second law specifies the relationship between force and acceleration. And we can finagle this mathematically by replacing acceleration with its definition. As you said, change in velocity over change in time. And one other change we can make, one other substitution. Here we've got a mass times delta V. What's that equal to?
Change in momentum.
Yeah, mass times change in velocity is change in momentum. So we can also say that net force, the total force acting on an object, is change in momentum over change in time. In other words, force is the derivative of momentum. The amount of force in total acting on an object tells you how fast the momentum is changing. In fact, this is actually how Newton defined force in the first place. When Newton was setting up all these relationships and terminology, definitions, and everything in the first place, he had just invented calculus, so he was still riding high on the idea of how awesome derivatives are. So he was defining everything in terms of derivatives. And force, he originally defined as the derivative of momentum. Force means how fast the object's momentum is changing. In modern textbooks, we usually write it like this instead because this is often a more practical way of doing the calculations. But this is an equally valid way of defining what force is, how fast the momentum is changing. You apply a force to an object, you're going to change its momentum. Unless, of course, there's another force canceling it out. Excuse me. Another useful thing we can do with this is solve for change in momentum. Isolate delta P here, and what do you get?
Net force times change in time.
Yeah. So that tells us that if you want to change the momentum of the object, you have to apply a force to it, and that force has to last for some amount of time. Furthermore, the amount that the momentum changes equals how much force times how much time it lasts. And that concept overall, the idea of force times time, is usually called impulse. You apply an impulse to an object, that means you're applying a force that lasts for some amount of time. The amount of impulse is the amount of force you're applying times how much time it lasts. That's often written as the letter lowercase j with a vector sign. Because this does count as a vector. Force has a direction, time is a scalar, so that doesn't change the direction. So impulse is a scalar, or sorry, impulse is a vector, and that vector tells you how much the momentum changes as a result of that force. So this is essentially instructions or a recipe on how to change the momentum. It also tells us under what circumstances would you expect the momentum to not change?
When the force is constant?
If the force is constant, specifically which constant though? What value does force have to be to make the momentum not change at all? Yeah, it's got to be specifically 0. If there's no force at all, then 0 times any amount of time is going to be 0 change in momentum. So this tells us furthermore that if there's no force, specifically no net force. Maybe there are several forces, but they're canceling each other out. If the total force on the object is 0, then the object's momentum does not change. Whatever its momentum is right now, it's going to continue to have that momentum forever unless some force acts to change it. Any questions on that so far? And moreover, this concept also applies to systems of objects. If you've got a system consisting of several objects, maybe interacting with each other, maybe not, the only way to change the momentum of the total system is to apply a force from somewhere else. For instance, if you've got several objects interacting with each other, let's say you've got 2 planets drifting by each other. Planet A and planet B. And let's say they both currently have a momentum. Let's say planet A has momentum, maybe it's going in this direction, and planet B has momentum going in this direction. Even if they don't contact each other, even if they're not crashing into each other, what forces are they going to be what force is going to be involved in their interaction? If so, you've got something the size of a planet, what force is going to be important here?
Gravity.
Yeah, these are going to be attracting each other gravitationally. So planet A is going to be attracted towards planet B. We're going to get a force on A from B. That force is going to change the momentum of object A. But meanwhile, what is planet B experiencing?
The opposite, like
Right.
in the
B is
opposite
going to
direction.
experience exactly the opposite force. Planet A is gravitationally attracted towards planet B, but planet B is also gravitationally attracted towards planet A. So this would be the force on B from A. And these two forces should be exactly the same strength, but in opposite directions. In fact, you could sort of think of these as the same force, just viewed, this is just one force, the attraction between the two objects, viewed from 2 different perspectives. And this is usually referred to as Newton's third law. Newton's third law is that it's often phrased as every action has an equal and opposite reaction, but I find that that's usually more confusing than it helps. It causes more confusion than understanding. So I think it's a lot more useful to just phrase this as forces come in pairs. A force is an interaction between 2 objects, and each one of those objects experiences that force in an opposite direction. A is attracted towards B, B is attracted towards A, with the same amount of force, but in opposite directions. Forces come in pairs. And specifically, we'd say that the force on object A from object B, or caused by object B, and the force on object B from object A, or caused by object A, are the same strength, same magnitude, but in exact opposite directions. So we'd write that as one of them equals the opposite of the other. So Newton's third law can be phrased as an equation. The force on A from B is the exact opposite of the force on B from A. Any questions on that so far? So as these planets drift past each other, what's going to happen to planet A specifically? If it's moving in this direction, but it gets a force in this direction, what's going to happen to it?
The direction's going to change?
Yeah, the direction's going to change. The path that planet A takes is going to curve. Likewise, planet B, it's moving, let's say, south-southeast, but it's getting a force west-southwest. So it's also going to change its path. Planet B, let's say it was moving in roughly a straight line. It's going to curve as it experiences that force. So these objects change their paths because of the forces. So which means each object individually is changing momentum. Planet A is experiencing a change in momentum because it's experiencing a force. And change in momentum equals force times time. Planet B is also experiencing a force for some amount of time, so it's also going to change its momentum. So the individual planets do change momentum as a result of this interaction. But if you consider these objects as one big system, what can we say about the total force acting on the system? If you just pretend for the moment that A and B are one big object.
Do they cancel each other out?
Yeah. If we look at this as just one big system, A exerts a force on B, B exerts a force on A. So if we treat these as separate objects, they don't cancel out. But if we treat this as one big system, if we just think of this as a collection of stuff, the system is exerting a force on itself. The system is exerting a force on itself. So if we look at this as just one big distributed object, the forces all add up to 0 because we've got these equal and opposite pairs. And usually you wouldn't add up forces acting on separate objects. But in this context of a system, we're treating this as just one big object. So there's no forces from anywhere else acting on the system. A is causing B's momentum to change, B is causing A's momentum to change, but those changes balance each other out. As individual objects are changing momentum, but the total momentum of the system does not change. In fact, the only way you can change the total momentum of the system is by applying a force from somewhere else. Like maybe there was a sun out here that was exerting gravitational force on both of them. The gravitational force from the sun would be coming from outside this system, so that would change the total momentum of the system. But if you're looking at a system of objects that are all interacting with each other, but not interacting with anything else outside the system, we would consider that a closed system, and the total momentum would not change. The individual pieces can change momentum because they're interacting with each other, but the total momentum of the system should stay constant. And this is where the whole idea of conservation of momentum and these momentum charts comes from. As long as you know that the total force acting on the system from elsewhere is 0. Either there's no forces from outside, or there are some forces from outside that they cancel out, then you can conclude that the total momentum of the system does not change. Maybe some of the objects change momentum in one direction and other objects change momentum in another direction, but all those changes cancel out. And this is a very useful way of being able to predict what happens after some sort of interaction, to figure out what's going on with these planets after they interact with each other. Or maybe you've got a couple of rocks colliding and bouncing off and you want to know what's going on afterwards. Conservation of momentum is a very useful way of dealing with that transition, the change from before a collision to after a collision, or before some sort of gravitational interaction to after. Any questions on that so far?
So in a problem context, would the problem have to tell you like neglect gravity in this situation or consider this a closed system for you to say that delta P equals 0?
Strictly speaking, yes. You would have to know that there's no external forces involved.
Okay.
And usually either that'll be specified or there will be enough context that you can assume that there's no external forces.
Okay.
Like a lot of the example problems you're going to see are probably going to be like collisions between rocks floating out in space.
Yeah, we did some with cars earlier, and then they said just make sure the track was frictionless.
Yeah, with actual physical real world collisions, usually the main complication is friction. That we have, that we're not really looking at a situation where there's no external forces. As anytime you've got an object sliding on the ground, there's always going to be friction. But you can often set up very specific cases where friction can be ignored. Like a common example is if you've got objects sliding on really smooth ice. There is friction, but it's a very, very small amount of friction. Or like an air hockey table. If you've got air blowing up from under the table and everything sort of resting on a cushion of air, then there's almost no friction. Or objects in free fall, if you just throw some objects and they collide, gravity is acting on them. But we're talking about, during the collision itself, we're talking about a very short period of time. So during that very short period of time, gravity is a fairly weak force, and we're talking about a very small amount of time. So the change in momentum due to gravity is going to be very small. But during the collision, the objects are exerting very strong forces on each other. So we've got very strong forces related to the collision times a short amount of time. Large force, small amount of time results in a more medium, moderate change in momentum. So the changes in momentum as a result of the collision itself are going to be significant. The changes in momentum as a result of gravity over that short period of time are ignorable. As opposed to, like, if these planets are drifting past each other, we're probably talking about a longer period of time than a fraction of a second. We're probably talking about minutes or hours or days. So it's really a matter of context there. Is the force large enough, and is it lasting for enough time that we have to consider the change in momentum that results? Any other questions on that so far? So let's try out some examples here. You sent me the FNT. Which problem on that were you specifically looking at?
Just problem number 1.
A collision where a cart sticks to the... No, wait, that's a different one.
I think if you scroll all the way down, you'll be able to
Yeah,
see
the rocket expelling gas at high speed for a short period of time.
Yep.
Okay, so let's take a look at rocket science. Rocket science is actually a lot less tricky than most people think it is. It's really just conservation of momentum. Rocket engineering is the tricky part. Building something that actually works, that's tricky, especially the plane. But rocket science, if we're just looking at why does a rocket move forward? At the most basic fundamental level, a rocket is just an object that's full of some sort of fuel. And how does the rocket propel itself forward?
It kind of shoots gas down, right? And the gas pushes
or not
back
necessarily down, but out the back of whichever direction it wants to go away from. So yeah, and typically what you do is you take this fuel and you burn it. And this is actually kind of the genius aspect of conventional chemical rockets. You need to have some sort of mass to throw it out the back. And you need some sort of source of energy to make that throw happen. As a typical chemical rocket, you've got fuel. You burn the fuel to create energy from the chemical energy in the fuel and use that same energy to push the exhaust out the back. So you're using the fuel both as a source of energy and a mass that you can throw out the back to push yourself forward. And rockets don't have to be that specific sort of thing. You don't have to be burning fuel and shooting the exhaust out the back. If you're just like standing on a skateboard and holding a brick and you throw the brick to the north, what happens to you?
You going backwards to the south.
Yeah. You're accelerating, you're creating a force on the brick to the north, so the brick pushes you to the south, equal and opposite forces. And that's technically a rocket. You are taking an object and launching it in one direction using the muscles in your arms as the engine, and that causes you to accelerate in the other direction. That's the basis of all rocketry. You're pushing something you don't need in one direction to cause yourself to be pushed in the other direction. And any rocket needs reaction mass, the thing you're throwing backwards to push yourself forwards, and an energy source, some energy that you can use to provide that push. With the chemical rocket, like I said, you're using the fuel to cause both of those. You've got fuel that you can burn to create energy, and then that fuel also leaves exhaust, which is the mass you're throwing backwards using that energy. And of course, there's other ways to do this as well. You could use some sort of inert gas as the reaction mass, the mass source, and some other sort of energy, maybe electrical energy or nuclear energy or something to throw it out the back. But you've got to have some way of throwing something out the back at high speed. In this case, I think we're just going to assume that instead of burning fuel, we're just going to treat it as pressurized gas. You have this container full of high pressure gas. You open a valve to allow gas to shoot out the back, and that propels the rocket forward. Basically the same principle as if you blow up a balloon and then let it go and it flies all over the place. It's shooting high pressure gas out the back to push itself forward. So let's take a look at before and after. Before, we've got a rocket with fuel, just I guess a container of pressurized gas. And are we assuming the rocket is moving yet or not?
I think the problem says it's at rest initially.
At rest. Oh, it says the rocket in part A, it says the rocket has an initial constant speed. So we're assuming, I think we are assuming it is moving. I mean, I guess the initial constant speed could be 0, but let's assume that it is already in motion. So let's assume the rocket is already moving slowly forward. We've got some initial velocity. But then we're going to expel gas out the back. We're going to open up the valve in this pressurized container. Let me just rename this gas instead, because it's not really fuel if we're not burning it. So we've got this pressurized gas in a closed container. But then we're going to open up that valve and allow gas to shoot out the back at very high speed. So we open up the valve. This pressurized gas escapes out the back. And the gas is now traveling backwards at some very high speed. The final of the gas. And as a result, what's going to happen to the rocket?
It's going to go at V final magnitude, but in the opposite direction.
Not exactly the same magnitude necessarily, though. It's definitely going to, yeah, it's moving. And notice that it was already moving to the right. But what's going to happen to its motion?
It'll go faster.
Right. Presumably it's going to go faster. V final of the rocket. I mean, this is ultimately the whole point. You're expelling gas out the back of the rocket to make the rocket go faster, or at least to change its velocity. Maybe you will do it in the other direction because you want to slow down, or maybe you want to change the direction of motion or something. But if we're just looking at this one-dimensional case, you've got a rocket moving to the right, and you shoot exhaust gas out the back to the left, then the rocket is now going to go faster to the right. So let's see if we can analyze that using this idea of a momentum chart. The idea is we're going to be considering as columns, we're considering the initial momentum, change in momentum, and final momentum of every object in the system. Initial momentum, change in momentum, and final momentum. And what are the objects in the system we need to consider here? Yeah, the rocket and the gas.
Why don't we write like P initial, then change in P, and then P final? Why not like P initial, P final, then change in P?
It doesn't really matter. It's just for consistency, I guess. Also, having it in this order, I think, makes it easier to look at it as initial momentum plus change in momentum equals final momentum. So we're looking at what you start with, what you end with, and then in between, we can look at how much it's changing. And you can just, so like if you have actual values here, you can just read across this value plus this change equals this final value. So I find it easier to interpret initial plus change equals final. Any other questions on that setup so far? And then also typically we want to include a row for total, because the total momentum is really where the magic happens. Total momentum is what's most predictable here. So this is typically how we're going to set up the momentum chart or momentum table. We're considering what's the initial momentum of everything, what's the final momentum of everything, and then how much is the momentum changing. Usually the final momentum is what we most care about, but it's often useful to fill in the changes as well to figure out what's going on during the actual collision or during the interaction. You're always going to want to include a total row. There's not necessarily always going to be two things in the system, though. You might have more than two things in the system, or the system might consist of just one object, in which case you don't really need multiple rows. You can just have one single row for the one object in the system. But in most cases, you're going to have two or more objects, a row for each object and a row for total. So let's see if we can fill in any of these. How do you calculate momentum? Yeah, mass times velocity. And the rocket and the gas, since the rocket and the gas are together, at the beginning, they're going to have the same initial velocity because they're moving together. The gas is enclosed inside the rocket. Does that mean they have the same initial momentum? No, because what could be different here?
The mass.
Yeah, they have different masses, presumably. You've got really two masses to deal with. We've got mass of the rocket. Let's call mass of the rocket capital M, and mass of the gas lowercase m. So that means the rocket's initial momentum will be big M times V initial. The gas's initial momentum will be little m times V initial. And we don't really know which one of those masses is larger. I don't think it specified that in the problem. But let's just make an assumption about that for purposes of being able to draw this out. Do you want to treat the mass of the gas as larger or smaller than the mass of the rocket here? Let's go with smaller, yeah. And by the way, in a real world scenario, a rocket, typically the mass of a rocket is mostly fuel. If you've got a rocket sitting on the launch pad ready to launch, something like 90% of its mass consists of fuel, because you need to spend a lot of fuel to get up to orbit. However, we can treat this as little m is the mass of the amount of gas we're expelling right now, just for this maneuver. And big M is the mass of the rest of the rocket and the rest of the fuel that we're not burning. So we're just burning a little bit of fuel to propel everything else forward. So let's assume that that big M is large and little m is small. That way, when we actually draw this out, the rocket has a, let's say it's going at a very slow speed times a large mass is this medium big M times V initial. And then the gas, same initial velocity times a smaller mass. So that'll be a smaller arrow pointing in the same direction. What do we get if we add those up? If you've got a vector to the right plus another vector to the right, what happens? Yeah, it's still going to be a vector to the right, it's just going to be larger. In fact, since these are in the same direction, we can just combine their lengths. So this will be, if we add these together, we can even factor out the initial and say big M plus little m times V initial. And I think that makes sense in light of treating this as just one big object. If you treat this as just one big object, its mass is big M plus little m times its initial velocity, tells you its total momentum. As for the after situation, well, before we get to the after situation, is there anything we know about the changes in momentum?
Can you assume that the total momentum has to be 0 because you're just looking at these two objects in the system?
The total change in momentum, I would say.
Yeah.
Because, yeah, we're just looking at these two objects. They're certainly interacting with each other as the rocket pushes off from the gas, but they're not interacting with anything else outside the system. We're assuming this is far enough away from any planets that gravity can be ignored. And also, this is presumably taking place over such a short amount of time that only very strong forces are going to matter. And there's no other very strong forces other than the rocket pushing off of its own exhaust. So yeah, I would assume here that we can treat this as a closed system. The change in total momentum is 0. And we would write that as a 0 with a vector sign because we don't really mean the number 0. We mean a vector whose coordinates are all 0. The vector is 0, 0. What does that tell us about the final total momentum?
Does it need to be equal to the total initial momentum and it's going towards the right?
Exactly. If there's no change, then the final value is the same as the initial value. And you can think of that in terms of this just reading across. Initial plus change equals final. Initial plus nothing means the final is going to be the exact same. However, just knowing the final total momentum doesn't really tell us how it splits up. We know this value plus this value equals the total. This final value plus this final value equals the final total. But that alone doesn't tell us how it splits up. So generally, you need one more piece of information to figure out how these are distributed to each other. And in this case, we know something about their final velocities. We know that the gas is expelled to the left at some high speed. So even if we didn't already know anything about the final motion of the rocket, let's say we fill in the final momentum of the gas. It looks like we've got again, a small mass, but it's being shot out the back at a very fast speed. So what does that tell us about the final momentum of the gas? Maybe not. We know that the mass is smaller than the rocket, but keep in mind, we don't know how these speeds compare yet. All we know for sure, in fact, let's say we don't even know this yet. We don't know what's going to happen to the rocket next. We know that gas is being shot out the back at some high speed, but yeah, it's definitely going to be going towards the left. The gas is being shot to the left at some very fast speed. So the final momentum of the gas is going to be to the left. The momentum itself might not be all that big because we're shooting it at a fast speed, but it's only a small amount of mass. So m times v final of the gas. But we can now figure out the final momentum of the rocket because what do we know about these two values?
They have to add up to P final total.
Right. These have to add up to the final total momentum. And if you've got some unknown value plus a vector to the left equals a vector to the right, what does that tell you about this value?
That it has to go towards the right and it has to be longer.
Exactly. It's going to have to be some large value towards the right because it's got to be not only enough to cancel out this vector, but enough to have some amount to the right left over. And this is all vector addition. This large vector to the right plus this medium vector to the left equals this medium vector to the right. They partially cancel out. And of course, if you have actual numbers, you can just fill those in. This is going to be, presumably this is mass of the rocket times the final speed of the rocket. So we could add these up. We could say the final value, big M times V final rocket. And since this is to the left, we'll treat its x component as negative. And we can set that sum equal to the initial total. And then you could actually solve that for V final of the rocket. So that tells us the rocket is going to be going to the faster to the right than it was at the beginning. And as for how much faster, we could actually solve for V final rocket here. Or more importantly, we could solve for the change in velocity. Because what's really important in rocketry is not the velocity, but how much the velocity changes during a maneuver. So if we set this up, we could say m V final rocket minus little m V final gas equals, and then if we distribute this, m V initial for the rocket plus little m V initial for the gas. We could actually solve this for how much the rocket's velocity is changing if we subtract big M V initial from both sides. And add this to both sides. So the delta V for the rocket, if we then divide by big M, delta V for the rocket, we've got little m times V initial plus little m times V final of the gas. We could factor out little m. So mass of the gas times initial speed plus how fast the gas is expelled out the back, divided by mass of the rocket. So if you want a lot of delta V for the rocket, if you want the rocket to change its velocity as much as possible, how would you arrange that? How would you arrange the mass of the gas, the mass of the rocket, and you can't really control initial speed, but let's say final speed of the gas. What choices would you make when designing the rocket to make the amount the rocket changes its speed as large as possible? Yeah, you'd want a small rocket mass, specifically small compared to what? What other mass?
To the gas.
Yeah, you want the gas to have a lot of mass and the rocket to have a little mass. So this is what I was saying earlier about how realistically rockets, the mass of a rocket is mostly fuel. The larger the fuel mass is as a percentage of the rocket mass overall, the more you can change your speed. And changing your speed is really what rocketry is all about. So realistically, you want to have most of the mass of your rocket as fuel. Also, we can control to some extent the exhaust velocity, how fast gas is expelled out the back in terms of meters per second, based on how we design the engine. What would you want to be true about the exhaust speed in order to get lots of delta V for your rocket? If you want the final speed of the rocket to be changed as much as possible, what has to be true about the speed at which exhaust is shot out the back?
Should it be pretty small?
If this is pretty small, though, the result is going to be pretty small.
Okay.
We have, I don't know if this is really very clear here, but mass of the gas divided by mass of the rocket times the initial plus V final of the gas. So the larger V final of the gas is, the more delta V you get for the rocket. And I think we can also see this in the differences here. If you subtract final minus initial to get the difference, subtract final minus initial to get the difference, these changes add up to 0. So the more the gas's velocity is changing, the more the rocket's velocity is changing also. The best rocket engines, assuming you don't need to worry about lifting off in the first place, once you're in orbit, the best rocket engines are the ones that shoot gas out the back at the fastest possible speed. It's usually called exhaust velocity or sometimes specific impulse of the engine. But that exhaust velocity, how fast you can shoot exhaust out the back in meters per second, is the efficiency of the engine. An engine that shoots gas out the back at very high speed is an engine that is very efficient in terms of how much push you get per kilogram of fuel you use.
Sorry, so why is delta P arrows the way they are written?
Sorry, what was that?
Why are the delta P values the way they are written over there?
Oh, I think I had those reversed actually.
Okay.
Because the rocket starts off with a small momentum to the right, ends up with a larger momentum to the right. So that's a change more to the right. Whereas the gas starts off with momentum to the right, but it changes to the left. So the change is leftwards. And again, you can think of this as addition. Initial value plus change equals final value. Or you can think of it as delta being a subtraction. The change is final value minus initial value. And it might help to think of these in terms of components. This is a large positive x component. This is a smaller positive x component. Large positive number minus small positive number equals a more medium positive number. But it's positive, it moves to the right.
And the change in momentum has to equal each other because of Newton's third law, right?
Exactly. That the objects are exerting forces on each other that are equal and opposite for the same amount of time. And again, the change in momentum equals force times time. So opposite amounts of opposite force, but same amount, times the same amount of time means opposite and equal changes in momentum. So yeah, the fact that these are equal and opposite is also directly due to Newton's third law. And the fact that due to conservation of momentum, we expect them to add up to 0. If you got two things that add up to 0, they have to be equal size in opposite direction. Any other questions on that? All right, try out this same approach of momentum charts using the other examples you're working on. Usually you're gonna fill in the initial values first and the fact that there's no change if you know that there's an isolated system. That means the final total has to be the same as the initial total. And then usually the difficult part is figuring out how that splits up. So you're gonna need one more piece of information about the final motion of something in the system. But give that a try, get some practice, have a good weekend, and I will see you next time.